This video is for Unit 5, assignment number 3, balancing equations using algebraic proportions. There are certain equations that you'll run across that become difficult to balance by inspection. So if you ever run across an equation that's difficult to balance, you might try applying this method. So balancing equations using algebra will work for any equation. However, I would reserve this method for use when really nothing else has worked for you. So I'm going to be solving question number 4 on assignment number 3. And to balance equations using algebra, we first begin by assigning each coefficient in the formula a variable. So I place the variables a, b, c, d, and e in front of each formula in the equation. We then use those variables to count the numbers of each element on the reactant and product side. And since equations have to be balanced, we can establish a statement, an equality that has to exist for the reactant and products of each element. For example, on a number 4, on the reactant side, if you look at carbon, there's one carbon in the formula, and that one carbon will eventually get multiplied by whatever number we put in for the variable a. But right now all I can say is that there's one a worth of carbon on the reactant side. If I look at the product side, I also find one carbon. That one carbon will eventually get multiplied by whatever variable I put in for e. At this point, all we have is 1 times e worth of carbon. But since the amount of carbon on the reactant side has to equal the amount of carbon on the product side, I can write this as an equality that 1a has to equal 1e when everything's done. I do the same for all of the other elements. 2a's worth of oxygen plus 1b worth of oxygen plus 2c's worth of oxygen have to equal the 2d's on the product side plus the 3e's that we also have on the product side. For hydrogen, 2b has to equal 1e, and for sodium, the 2c's have to equal the 1e. At this point, we can really assign any of those variables a number, just making an assumption. And in this case, I'm just going to assume for variable b that it is a 1. I'm using variable b because it shows up in multiple equations. And so if I assume that b is a 1, I can take that assumption and apply it to the equation for hydrogen. That equation says 2b, which now is a 1, is equal to 1e, and if we solve for e, we find that e has to equal a 2. So this is just established that if b is a 1, that e will be a 2. Now that I have e as a 2, I can insert that 2 into any equation where e exists, either for carbon or sodium. I'll do it for both of them. The 1a in carbon has to equal 1e, which is now a 2. And solving for a, we find that a in this case also comes out to a 2, which makes sense that 1a equals 1e, which says really that whatever a is, e has to be the same number, and in this case they're both a 2. In the equation for sodium, 2c equals 1e, with e being a 2, 2c equals 1 times 2, or 2c equals 2. Solving for c, we get an equation or the answer that says c equals 1. So I've established, based on the assumption that b is a 1, that a has to be a 2, c has to be a 1, and e has to be a 2. And I can take all of those and insert them into the equation for oxygen that has a, b, c, d, and e, and use that to solve for d. replacing the variables with their values, 2a plus 1b plus 2c equals 2d, which I don't know a value for, plus 3e. And I'm going to solve for d in this case. 2 times 2 is 4, so that 4 plus 1 times 1 is 1, plus 2 times 1 is 2, equals 2d plus 3 times 2, which is 6. And on the left side I have a total of 7 equals 2d plus 6. Solving that for d, subtract 6 from each side, I get 1 equals 2d. And solving for d, I actually get a fraction 1/2 for d. Now that's okay that we ended up with a fraction, however we can't leave any of the coefficients in fraction or decimal form. So if you ever solve for variables and end up with a fraction or a decimal, you need to multiply that into a whole number. The rule says that if you multiply a fraction to create a whole number, that what you do to that fraction you also have to do to all of the other variables. So to turn a half into a whole number, we can multiply it by 2, and 1/2 times 2 is 1. But since we've done it to that variable, we also have to do it to the others. Which means my a is going to become a 4, my b is going to become a 2, my c is going to become a 2, and my e is going to become a 4. And I get the variables 4, 2, 1, and 4. And even though I have an answer for each variable, I think it's safe to always go back and insert those answers into the variables that they represent and count the equation to make sure that each of the elements does add up on the reactant and product side. So putting a 4, 2, a 2, a 1, and a 4 in for each variables and counting, you will find that each of the elements does add up and that this reaction is balanced. So with that, if you'd like to go back and try numbers 1, 2, and 3 above using this process and see what you get. With that being said, I will tell you that one of the problems listed above does have a typo that even though it's solvable using the algebraic proportions, what you get for an answer doesn't actually balance the reaction. So if you happen to find where the typo is in any of the problems above, please send me a message. You can private message me through Google Classroom, and I'll apply some extra credit to your work.